ecology. Charlie.
Thank you, Jeff. And thank you, John, for the exercise this morning showing our geographic diversity. That's some of what I'll be touching on in here as well. So that's a good lead-in. The question I'm addressing is this notion of whether a trend that we've found in mountain precipitation is important. So certainly we know that trends in climate may not predict the future, but is it important in interpreting the past? So trends that we've seen in outcomes that might be related end up calibrating our expectations, whether those are directly calibrated through calibrating physically based models, empirical models, or even just the mental constructs that we use to understand how the system might work on a more emotional level, in a sense. So what happens when we attribute causality of precipitation-induced trends to temperature in particular? So the first place probably to start is to begin with what are the trends going on in mountain precipitation? What's the evidence we have for those? And the period looking at here is 1948-2013. So any trend, we really do need that time period, as Phil showed us yesterday, to know what the context is. But what we see here across these mountain watersheds, some of the last relatively undeveloped watersheds across the Pacific Northwest, mostly out of mountains, are showing pretty substantial declines in runoff, most strongly in the driest years, but also just in general, if you average over that space, about a 20% decline over the course of 60 years. We had questions as to why. Certainly evapotranspiration came up as a good suggestion. And I'll point out in the next slide why that was one of the first places we went to look. But if we look at the energy needs for that, we also have to have an energy balance as well as a water balance. And if we look at the energy balance, this is the additional available heat coming in as a result of climate change. 1.8 watts per square meter, driven by the additional gases, greenhouse gases. And if we add into that a few other sources that we can add for more net radiation coming in, snowpack disappearing for 2 weeks, gives you a little bit more energy to work with as well. We still can't quite make up for the range of decline. So if we look at evaporation, you can convert that directly to an energy number, and that's on the right-hand axis there. But if we just look at our available sources of energy, we can't make up for, if this had all been evaporated, we'd have to have cooling. That's the simplest explanation. There are also additional supports to that point. On the other hand, if we take a look at the precipitation data, so here's all the trends from the HCN2 gauge network across the Pacific Northwest, about 120 gauges. And yes, there are a few statistically significant ones in there, but about 10% of the gauges are showing a statistically significant trend with an alpha of 0.1, which is what you expect by random chance. So again, the field significance of precipitation change is not changing. Fundamental lesson here is if you only have two hypotheses, don't test them both. But the real piece to learn from that as well was to come up with the other hypothesis here, which is that those HCN2 gauges are not measuring the same places as the watersheds. So if you notice here, the watersheds, that same network of precipitation gauges are the black dots, and they meticulously avoid these stations. And those are the long-term gauges, those round, the black dots are the long-term gauges. So those where people have lived for a long time. Those tend to be developed locations. The watersheds are not developed. So there's good reason that these two disagree. So then the question is, and what we need to demonstrate is that what's going on in those watersheds is different than what's going on at those gauges. One of the possibilities for that is that we're dealing with a question of orographic precipitation enhancement. So you take wind, you push it up, the moist air up over the mountain mass, you condense the water, produce precipitation. If you change that wind speed, you would be expecting to change the amount of precipitation. And there's been some work done on that previously, but what we need to do to convince ourselves that these are related trends is A, demonstrate that what's going on in the mountains would be related to the wind, and the wind has a trend. So we'll start with what's going on with precipitation gauges in the mountains. So we've had snow-tail gauges up there on the order of 20 to 30 years. So if we take those and correlate them to the history of wind speeds, what we can find is if we're looking at the snow-tail gauges that are the squares in there, they're also mostly the red squares at the higher elevations along the Cascade Crest and the crest of the Rockies here. That's certainly places where we're seeing a good correlation between precipitation measured at gauge, even though it's an 18 to 30 year period of time, so we can't use those same gauges for looking at trends, but we can get the correlation sense of the wind. And then we can look at the wind speed changes, and we see a trend in those very similar to what we see for trends in the runoff from those watersheds. This supports the hypothesis. It's still a hypothesis, and in part want to get it out there to get it discussed more, because it really is still just at that hypothesis stage, and certainly a piece we need to understand. But there's a good stout reason for expecting that precipitation has declined over the last 60 years in our mountains. So why does this matter? I'm going to go through two examples, snow and fire. The example for snow is pretty obvious. People know this story well. There's less snow. We have warmer temperatures, we have earlier stream flows, and we have lower summer flows. The prescription that has been developed for addressing that is to store water behind dams instead of in snowpacks. One of the speakers yesterday, in fact, brought that up. But I know in Idaho at least, there are at least 3 dam proposals already on the table, in part linked to climate change, which is a particular irony there. So to back up now and begin to think of, well, why is this important? So people have been seeing these papers since the mid-2000s, early 2000s, the Model 2003, showing the declines in snowpack, and related one, the Stewart et al., showing the earlier timing. Managers have looked at the magnitudes of these trends and said weeks earlier over the course of these 40 to 50 years in these, so these have a similar time vein in them, the mid-1940s forward. And what was also published at the same time is precipitation is not changing. That's the story that we're getting from our HCN2 gauge network, and Phil explained that again yesterday. That is what we recognize as a system at the moment. So they're seeing that, they're attributing the whole story of these weeks of change to precipitation. So I want to look at another change that's going on, just because I could then do some attribution with it. Looking at the 7Q10, which is the 1 in 10 year weekly minimum flow. These are the low flows in the summer months. And they are also showing a trend, as you'd expect, along with timing changes and snowpack changes going down. But beyond that, we can look at the sensitivity of those over the last 60 years to precipitation changes as compared to essentially temperature changes. So on the vertical axis there, the center of timing, and looking at the net effect from that is essentially a temperature indicator. The bottom axis, the annual flow effect, is essentially a precipitation indicator. And we see that many of the basins, particularly the snow-dominated ones, are more strongly controlled in this historical period by the precipitation changes as opposed to the temperature changes. And then we see that there are also quite a few gauges in here that are really showing no relationship to either one. Good information as well. So let me explain why we might expect to see that kind of sensitivity going on within these gauges. This is a model, an empirical model of snowpack sensitivity, and it's a pretty simple story. These are contour lines of what you can think of as a pile of snow. On this axis is precipitation, on the bottom axis is temperature. And if you are cold and wet up here in this corner, you have a lot of snow. So we have high numbers here on the contour lines. If you're on this bottom axis, you're dry and there's no snow. If you're along the right-hand axis, it's warm and you have no snow. So you can get no snow one of 2 different ways, but if you want to have a lot of snow, there's only one way to get there. And if we want to look at these, now we grab these contour lines and we can begin to look at sensitivity. So for example, if we walk north on this topo map, i.e. in the direction of precipitation increasing, we see a very steep hill at this cold end of the scale. Go over to the other side of the graph and you see that there's not a lot of precipitation sensitivity when you're getting warm. On the flip side, if we're looking at temperature sensitivity, if you're out here in the cold land, you're walking along the contours. You're not really having a lot of sensitivity until you get out to this warmer realm of things, and you can see that if you're warm, you're very temperature sensitive. So if this round circle is more like is a set of stations, many of which are in the Cascades, and on the bottom here are a lot of interior stations, so more in Idaho, Montana, that kind of location. And when we plot a map of the sensitivity across this western U.S., this northwest, but western U.S. on whole, we see that the Cascades are just exquisitely sensitive. There's going to be a response there. Whereas if you look around, and I'd like to point in particular in this area in the Snake River Plain, second only to California in terms of the amount of irrigation going on. So a huge demand for irrigation water in this area. And we're seeing stations that aren't nearly as sensitive to temperature change. Still sensitive, still responding to temperature, but really we're looking at numbers more like 20 to 30% instead of 100%. And yet those early pictures showed us a geographically uniform picture that the people were responding to. So what we can learn from this picture then at this stage, there are things that managers could do short of dams if they're thinking about this. But if they think that the only thing impacting them is temperature, and they're looking at those graphs, they're doing the quick mental calculation of, okay, I get 2 weeks for a degree of temperature change. Let me just multiply that times 4, and bang, I've got 2 months of earlier streamflow timing, as opposed to looking at these more detailed maps. So it's just using that sort of construct, we can see where we can go awry. Likewise, if we take a look at futures of precipitation, again borrowing a figure that Phil showed yesterday, precipitation in the future is uncertain. This doesn't change that story at all. And the question then for the managers, if precipitation goes up, can I use that last map, or if precipitation goes down? So if precipitation goes up, and we look in these basins around the Snake River Basin, we can actually almost make up for the fact that the temperature increase has occurred. If we have, so this is plus or minus 7.5%, it's a ratio is what I'm plotting here. So in the denominator is what goes on for a 3 °C increase in snowpack, and the numerator is the amount of uncertainty we have due to precipitation, just plus or minus 7.5%. Which is about a standard deviation in that last figure. But in any event, it's saying that around that Snake River Basin, we're really looking at places where you can make up for it by increasing your precipitation, or if you keep losing precipitation, you can actually get into a much more dire situation. So we need to look at that side of it as well when we're looking at what precipitation can and cannot provide in the future relative to what temperature does. A second example relates to fire. Again, we've seen more fire in the landscape. It's been attributed largely to warmer temperatures, longer fire seasons. The Westerling paper is an example in there. And it's also been attributed to the fact that we have more fuel on the ground because we've had a lot of fire suppression. The prescription has been, let's thin the forests, all of the forests. And that's the key piece there. Again, spatial heterogeneity is an important story. This is from a Botsoglu and Colden, 2013. And what we see on the right-hand side are the precipitation. The hash marks in here represent the fact that it's a negative trend versus a positive. And on the left side is the temperature correlation. The R-square values are shown for scale on the bottom. And the story they tell in there is that the precipitation sensitivity for fires across the Pacific Northwest is stronger for the most part than the temperature. And they provide quite a bit of explanation to go with that. But that's the simple story we'll stick to for now. The vertical side of this is saying the number of months you're looking back. So the upshot of this story is really more related to spring precipitation than the winter precipitation. Now let me go to not quite so strong of an example, but the Westerling story is that we have temperature increases which change our snowpack, which change our runoff timing, which give us a greater fire extent. Now if we add precipitation into that, the Holden et al. Paper does that, we actually can see if we look at these metrics at the end that about 3 times more information historically has come through the precipitation pathway than through the temperature pathway. On the other hand, if you look at these numbers compared to the ones in the Botsoglu and Colden one, this is a pretty poor model of what fire does in comparison. So it's kind of one of the not so good correlations on their precipitation graph. But it still tells us that precipitation does have an influence on fire. And we probably all know that at some basic level, even though we're being told that temperature is the only thing that is changing. Now to add to this, I'll grab this from the Dillon et al. 2012. They did a paper on fire severity. They looked across the whole West, but here's from the Pacific Northwest. And if we look across the West, really, the Rocky Mountain region, the one in pink there, is the big dog in terms of the amount of fire. And when we look at that, we see that the fires that happen in that region, and especially the severe fires, are fires in the cold forest. And what those cold forests look like are these big, broad expanses, largely of lodgepole pine, spruce, those kind of nice high elevation species. And these are in places where, as I showed in the early examples, temperature is not making a big impact on what the snowpack does. And really the precipitation trends have a lot more sensitivity up there. And you can see one of those big fires in the background there. These forests burn big. They burn hot. That's how lodgepole pine reproduce. That's their ecology. And if we dig in and take a look at these forests in detail here, we see a lot of fuel laying on the ground. We see thin-barked trees. And yet a prescription for thinning these is what's being thrown out there on the basis of thinking that we have a temperature issue primarily. And yet that's not something sustainable. If we thin this, we'd have to go thin it again by hand. It's not something that could be maintained by, say, prescribed fire. This is the real model that thinning idea is tied to, and that's these ponderosa pine forests. And yes, in the past, that's the dynamic there. We can go in and treat those, and then we can let wildfire continue to maintain those, the small, low-level fires. So just in closing, the attribution of past changes influences our future expectation. People like analogs. The past is clear now. Mountain precipitation has declined, and it's likely influenced our fire and snow trends. But future temperature changes are we expect to be quite a bit larger than they have been, and precipitation futures are uncertain. And so my argument is that clearly separating past precipitation and temperature roles in what has gone on can help us design more robust adaptation measures. Thanks much.
We have time for questions. If you could come to the mics to ask them. I guess everybody's convinced. Okay,
No,
well, let's thank
Great.
Charlie again.